We are now going to conclude all the topics for chapter 20. Continuing talking about the reactions for esters. Esters can undergo reduction with the use of lithium aluminum hydride. And as you can see outlined on the top of the slide, an ester in the presence of excess lithium aluminum hydride will form a primary alcohol. There is another organic byproduct that is formed in the reaction, which is going to be the group that is bonded to the single bond oxygen is going to be forming an alcohol in the process. Okay? Now, understand that in this mechanism, as we have seen previously, lithium aluminum hydride is going to be a source of hydride ion. So in the first step of the reaction, we're going to have the hydride ion do a nucleophilic attack to the carbon in the carbonyl, and the electrons are going to go up to the oxygen. After the formation of that tetrahedral intermediate, because we are under basic conditions, the oxygen anion that is formed is going to try to reform the carbonyl. So in turn, that O alkyl is going to be expelled from our structure. We are going to be forming at this point an aldehyde. And we already have seen previously that aldehydes in the presence of the lithium aluminum hydride reagent, it doesn't live. So what happens is that it continues to being transformed. So then that aldehyde gets a second nucleophilic attack by another hydride ion. The electrons go off to the oxygen, and as you can see, that last proton transfer, that's because of step number 2, which that alkoxide anion that is formed, it gets protonated to give rise to that primary alcohol. Understand that similar to what we have seen previously for acid anhydrides, and we have seen for acid chlorides, we can have the formation of the aldehyde. So we can actually stop at an aldehyde by utilizing a modified reagent, okay, that is going to be in a way cousins with lithium aluminum hydride. So understand that the reduction of an ester can be stopped at the aldehyde by using diba instead of lithium aluminum hydride. Diba specifically is going to be the structure that we have here, which this is diisobutyl aluminum hydride. That's the name of the reagent. And as you can see, by using that as step 1, followed by a workup, we can form the aldehyde. And similar to what we saw in the previous reaction, that group that was bonded to the single bond oxygen alkyl is going to turn into its corresponding alcohol. Esters can also react with Grignard reagents to form a tertiary alcohol. This is something that we have seen previously with acid chlorides and with acid anhydrides. The mechanism for this conversion goes as follows. We're going to have an ester, and then our Grignard, remember that that is going to be a source of R minus, is going to add that nucleophilic group that comes from the carbon in our Grignard. Is going to add to the carbon in the carbonyl in our ester. As we have seen previously, the electrons are going to go up to oxygen. Now, because we're under acidic conditions on that first step, we can actually propose that the electrons, when they come down from that oxygen that is negative, is going to have that O-methyl being kicked out as the leaving group. We are going to be having right there the formation of the carbonyl group once again. Now, As you can see here, once that occurs, we are forming a ketone. And as we have seen previously, ketones, in the presence of a Grignard reagent, they can be substituted one more time, and that's exactly what we see. There's a second nucleophilic attack from our Grignard reagent and the formation of that alkoxide intermediate that in step 2, which is the workup, we are going to then protonate the oxygen that is negatively charged, that is formed from that second nucleophilic attack from our Grignard reagent, and that's what results in the formation of a tertiary alcohol. We are now going to be focusing on the preparation of amides. When it comes to amides, as we have seen previously by discussing the reactivities of acid chlorides, acid anhydrides, and esters, by now we have different ways in which amides can be formed. So as is illustrated here, carboxylic acids derivatives are going to give rise to the bottom functional group. So you can have amides formed from acid chlorides, acid anhydrides, and ester. So those are different ways that we can make them. The best way is by utilizing the most reactive, but we have illustrated in previous discussions from this chapter that there's different ways that we can accomplish the synthesis of amides. Now, the most popular way to make an amide is from an acid chloride with the corresponding amine. So remember, depending on this section of the molecule, meaning if you want your nitrogen to just be an NH2, or if you want it to be substituted, that is going to affect what type of amine you're utilizing, either ammonia or a substituted amine. Always understand that in order to accomplish this reaction, we need 2 equivalents. That is necessary because 1 4 equivalent in this reaction is going to be utilized to neutralize the HCl byproduct that is formed during the reaction. Amides can be hydrolyzed. So when amides are hydrolyzed, that happens under acidic conditions. As you can see, in this hydrolysis process, it is important to note that we need a source of acid, and here we can have it illustrated by hydronium, but very important, we need to heat the reaction. The products of that reaction is going to be the formation of a carboxylic acid, and the ammonium ion. So it is very important, as I just mentioned, that heat it is utilized. Now, the products are favored at equilibrium because once we have the formation of the amine or the ammonia in this reaction, it can be protonated, okay? So once it gets protonated, then it cannot be acting as a nucleophile to reverse the reaction. Let's now go over the acid hydrolysis of amides. So this is the mechanism for the reaction. Because we're under acidic conditions, the first step of the reaction is going to be the protonation of the oxygen atom. And as you can see, now then that step, that first proton transfer, is going to make our amide a better electrophile. Then water is going to be functioning as a nucleophile and attack the carbon in the carbonyl of our amide. So we're adding a water molecule, and in the proton transfer, we are just deprotonating the water that came as a nucleophile in that second step. Because we're under acidic conditions, we cannot propose that NH2 is going to be leaving, because NH2 negative is going to be a strong base. So we need to propose the release of that nitrogen with the hydrogens as a molecule that is neutral. So that's why you see that in that third proton transfer, we are going to protonate the nitrogen so it can leave as ammonia. So what we see when we are releasing that ammonia from our molecule is that the oxygen atom, one of its lone pairs, come down to reform the carbonyl, then ammonia leaves as a leaving group, and that ammonia that is produced of that second to last step comes back and deprotonates the carboxylic acid to give rise to the carboxylic acid and the ammonium ion, as it was illustrated in the previous slide. Amide hydrolysis can also happen under basic conditions. When that occurs, as you can see in the first step, we're going to use strong base and heat, and then we're going to have an acidic workup. When it comes to the reaction itself, understand that the base catalyzed hydrolysis is even slower than when acidic conditions are used. So the mechanism for this process is going to be analogous to the base catalyzed hydrolysis of an ester that we have seen previously. And in the product of this reaction, as you can see, we are going to be forming a carboxylic acid. And along with this, remember that we're also going to be producing that ammonia. It's just that it wasn't illustrated here in the product. But understand that the ammonia is going to be produced too. Now we are going to be exploring the mechanism for basic conditions of hydrolysis of an amide. When we are under basic conditions, the first step of the reaction is going to be the nucleophilic attack of the hydroxide ion to the carbon in the carbonyl, and the electrons are going to go up to the oxygen. Once we make that intermediate, that tetrahedral intermediate, because again, we're under basic conditions, then understand that under basic conditions, then the oxygen that is negative can come down, reform the carbonyl in the molecule, to then expel or exit out that NH2 minus. Again, that can happen because we are under basic conditions. So if you're under basic conditions, bases can be proposed to be being expelled from molecules and be present as leaving groups. Once that occurs, understand that that NH2 that is negatively charged is going to come and act as a base, deprotonate the carboxylic acid. So in the first step of the reaction, you're going to be generating a carboxylate ion, which, as you can see, this is the structure. And I just mentioned, remember, the ammonia wasn't in the previous slide, but it is formed. So understand that what happens is that, as you saw in the previous slide, we need an acidic workup, because what happens is that since you form a carboxylate, then it needs to be protonated. So that's why, if I go back to the previous slide, on step 2, we have a step of acidifying or doing an acidic workup, because to generate the carboxylic acid, since in step 1 we produce a carboxylate, step 2 is just protonating it. So remember that in step 2, That's how we form the carboxylic acid. When it comes to amides, understand that they can be reduced utilizing lithium aluminum hydride. And that is a topic that we have seen throughout this chapter. Now, in the case of amides, when they are reduced with lithium aluminum hydride, as you can see, what we're going to be forming is their corresponding amine. Now, when it comes to the mechanism for this reaction, it's actually quite different from the others that we have seen in this chapter. The carbonyl group for this mechanism is completely removed, okay? While the nitrogen remains bound to the molecule. So understand that the arrow pushing mechanism that we have seen previously does not apply for this specific reduction of lithium aluminum hydride on an amide. Now, remember that because it wasn't illustrated and it wasn't in the slides, you're not responsible for knowing the lithium aluminum hydride reduction of amides to amines. Now we're going to proceed to deal with the last carboxylic acid derivative, which is nitrile. And first we're going to learn how to make them. Okay, so nitriles specifically, if you recall from first semester organic chemistry, can be made when you have this nucleophile react with primary or secondary alkyl halides, and then this reagent, that's just sodium cyanide, that's going to act as a nucleophile, and the reaction overall is an SN2 reaction. Now, understand that nitriles can also be made by dehydration of a primary amide, okay, using a variety of reagents, including SOCO2. So as you can see, as long as you have a primary amide, meaning that you're going to have an NH2 on the nitrogen side of our amide, and you react it with SOCO2, that gives rise to a nitrile. The mechanism for that primary amide dehydration goes as follows. As you can see, in the first step of the reaction, we have a nucleophilic attack, okay, by the amide itself. So the lone pair on the nitrogen is going to go and form a carbon-nitrogen double bond. Then one of the bonds between the carbon and the oxygen double bond is what's going to act as a nucleophile and attack the sulfur and the thionyl chloride. As we have seen previously, what happens is that oxygen atom that is present in the thionyl chloride comes down and reform that oxygen sulfur double bond, and in this case is going to make a chloride ion leave from the original thionyl chloride. Then on the next step, we're going to have a proton transfer. We're going to have a base remove a hydrogen specifically from the nitrogen atom, and that's going to put the electrons back on the nitrogen. And in the last step of the reaction, we are going to have the base, okay, then extract another proton from the nitrogen, then that is going to form that triple bond on the nitrogen, and we have this whole group leave the system. And remember that group actually is going to degrade to make sulfur dioxide, and it's going to make the chloride ion. Nitriles are hydrolyzed to carboxylic acids under acidic conditions. And as you can see in this process, the nitrile, when you put it in acid and you heat it up, is first going to make an amide, and then that amide is undergo hydrolysis to form that carboxylic acid and that ammonium ion. This is the mechanism for the hydrolysis of a nitrile under acidic conditions. In the first step of the reaction, our nitrogen atom is going to be protonated. Then the water molecule is going to attack the carbon that is triple bonded to the nitrogen. And as you can see, then we are going to make a molecule in which, if I highlight the carbon atoms, this carbon atom right here, this carbon atom right here is placed right here. Then we are going to have another proton transfer in which a water molecule is going to act as a base, remove a hydrogen atom from the water that acted as a nucleophile. This is our carbon atom. I just want to keep track of it. Then the lone pair on the nitrogen is going to go and extract a proton from hydronium, okay? Once that molecule form, understand that we're going to have a resonance stabilization for the nitrile, okay? And in the last step of the reaction, then what's going to happen is that at this point, another water molecule is going to extract the proton from the oxygen, and that's what is going to form our amide. If this is not clear, if I redraw, which this squiggly line arrow is my redraw, this is the same thing as drawing it in the following way. So they are the same molecule. So that's how we form that first part of the amide. Remember that when we have that amide, we previously discussed how they can be hydrolyzed under acidic conditions. And that's what results overall in the formation of the carboxylic acid and the ammonium ion. Nitriles can also be hydrolyzed under basic conditions. And when that happens, again, we are going to be generating a carboxylic acid. In this process, we are again going to need an acidic workup to obtain the carboxylic acid, because when we're under basic conditions, remember that we're going to, in that first step, form a carboxylate ion. So the acidic workup is basically to protonate that carboxylate ion. This is the mechanism for the hydrolysis of nitrile under basic conditions. So, as you can see, this nitrile is first going to be attacked by the hydroxide ion. And again, we're under basic conditions. And the carbon that is triple bonded to the nitrogen is the one that is going to receive the electrons from the nucleophile. Then is going to break one of its pi bonds and put it onto the nitrogen. Then, since we have formed a nitrogen that is negatively charged because it has those two lone pairs, that nitrogen is going to be removing a proton, okay? It's going to be acting as a base. Once that occurs, then that OH minus goes and extract a proton from the oxygen atom that actually came from the initial attack of the hydroxide. Then we're going to have a resonance stabilization, and then our resonance structure is going to be protonated to, again, we're going to go through an amide intermediate. Once you have an amide, as we have illustrated previously, that amide is going to be transformed overall to a carboxylic acid. Remember, we are going to make the amine, it's just that in the previous slide it wasn't illustrated or drawn in. Another reaction that nitriles can undergo is a reaction with Grignards. When that occurs, understand that nitriles are going to form a ketone. This reaction, as you can see, it has two steps. So specifically, that R group that is coming from the Grignard is going to add to the carbon that was triple bonded to the nitrogen. And as you can see, we have an acidic workup. So understand that in this process, that hydronium second step is added to form specifically an imine. And this is actually then hydrolyzed with this excess H3O plus to form specifically the ketone. So that's just how the whole process actually occurs. Similar to what we have seen previously, how carboxylic acids and many of its derivatives can actually react with lithium aluminum hydride, nitriles can also be converted to their corresponding molecules, which in this case is going to be a primary amine. So the reaction of a nitrile with lithium aluminum hydride results in the formation of an amine, as you can see illustrated in the reaction that we have specifically in this slide. So the takeaway message of chapter 20 is that carboxylic acids are very diverse, very reactive molecules. And as you can see in this slide, we have an overall view of the carboxylic acid. So I'm just going to label this. So we have the carboxylic acid as our main functional group. Then we have the derivatives. Starting with the acid chloride, acid anhydride, ester, amide, and nitrile. One of the things that it is important to note in between these is the interconversions, okay, between the different derivatives to each other. But overall, all the reactions that were presented in this chapter are going to illustrate how the parent functional group is a carboxylic acid. Then we have at least 5 main groups that are derived from that carboxylic acid. In addition, we saw how these derivatives from the most reactive can be converted into the least reactive, and we even have some functional groups that are going to be in a way made through similar carboxylic acid derivative reactions. So overall, this slide summarizes all the reactions that were discussed in this chapter.